5 and 6 over vacation, because from my reading of your projects, it appeared that what I was asking for was not clear, okay? So anytime I see that some things, like a majority of people aren't clear about it, I think there's a problem with how I've worded it. So let me just tell you what I was wanting you to do here. Maybe it's easier to tell you what I wanted versus, and then we'll go over the language. So I'm just going to use someone's project here. They were looking at the number of years since 1996. So their first column was the number of years since 1996. So they started with the year 1996 because 0 years from 1996, 1, 2, 3, 4, 5, blah, 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 up to 9 years after 1996. And on this side, they were looking at a population in the number of people in millions. And in millions is the unit. So 3.89, 3.88, blah, 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 4.14. Okay. So the first thing I just want to point out is that some of you just handed me in a data set. You never even told me anything about what data you were looking at. Okay. So you should have had some description. I didn't take off for it this time, but I just saw a table. A lot of you never even told me what your input was. Especially, most of you had some type of time measurement here. And I had to calculate for every single person to check your R values. But some of you might have put in 1996, 1997, 1998, and some of you might have done something like this student did. So if your graph didn't tell me, on the graph, you might have had for your horizontal axis number of years since 1996. Then I knew what you put in. Or some of you actually put it right in your table. So you need to tell the investigator or the person you're handing your model into what the heck your independent variable is. And so I need to know what you put in your calculator. So if you didn't do that, please go back and do that. But here's the problem. The problem was how you interpreted 5 and 6. This is what I wanted. The language says, use your model. So let's say you have a model, and I'll use a model here. And remember, I put that little Y hat on there just to show that it's a prediction, but you didn't have to do it. So here's the person's model. Okay. X is the number of years since 1996, and Y is the population, right? In millions. All right. So what I was looking for was I wanted you to make a prediction using your model, but I wanted you to make the prediction where you actually knew a value for the input variable. So notice you have 10 input values here where you know what the actual the output is. So I wanted you to pick one of your known points. For example, here's a known point. You know the value of your input here. The value of your input is 1, meaning the year 1997. I wanted you to put the 1 in here and use your model to predict the population. Then you could look and say, hey, I got a number pretty darn close to the actual data value. My model must be pretty decent. Or, wow, you know, I used a line to predict this. My actual predicted population is very different than the actual population. Maybe I should be thinking of another model. Okay, that's the sort of thing I was thinking about. So that's number 5. Number 6 says take an actual output value. So then you might pick something like this, 4.14 million. And then you would substitute that in for Y and then solve for X using your model. Right? Now you're solving for X. So then you actually get to see how many years after 1996, your model predicts your population would be 4.14, and then you can compare it to your actual piece of data. All right? So remember, these are the actual data points that you put in your scatter plot. The model will give you a prediction or an estimate either for an input value or for an output value. You can either estimate your population or you can estimate how many years. So I just wanted you to pick one data point, you know, like one input value and one output value, and see how good your model was, basically. So given that it was clear to me that you didn't understand that, you all can hand in 5 and 6 again, okay? And what I don't want you to do is to erase what was there, because that's the only way I can tell how I graded it. So do a little sheet of paper and do 5 and 6 over again. Any changes you make on a separate piece of paper. Then just float it. Notice you all, if you didn't have a paper clip or a staple, I gave you one. So just hand that in on Monday after vacation. Is everybody clear on that? Okay. Okay, how about if I check with you right after class, okay? If I want to kind of get on with class, but right after class, I'll check with you, all right? Now, the other thing I want to point out is if you start a graph at anything other than 0, you need to have a break in your graph. You need to indicate a break. I thought I had a web page up here, but I don't. So in other words, if you, for example, let me insert a quick graph here. I don't want anything on there. Well, I'm just going to draw a quick graph. So let's suppose you had this graph, okay, and you wanted to start your y-axis at 4 million. Well, clearly, you're not going to start a scale from 0 and try to go up to 4 million, right? You're probably going to use some type of increment, like let's suppose your population was usually in like 1/10 of a million. You probably would be starting, your first line might represent 4 million, and let's say your next line might represent 4.2 million, whatever your increment was. Anytime you start any of your scales at something other than 0, you must indicate that by what we call a break in the axis. So in other words, when you draw this graph, you go like this. It looks like a Z, backward Z. Some people will use just parallel lines like this to indicate the break, and that's okay as well. Some of you needed a break in both of your axes. It would be like taking, like your graph is way up here at 4 million. It would be like taking scissors and cutting out the line, your vertical axis between 0 and that, and just scooting it down. You're just shifting it down. So you always need to indicate a break when you draw a graph. The other thing you should always have is a title on every single graph you ever produce. Person should be able to look at a graph, read the title to know what the data is about, read the axes, know what your different variables are, and the units that's measuring those variables. Okay. So if you hadn't learned some of those basics in a class previous to this or in high school, those are just some of the basic things that every graph should have. Okay. Yes, Michelle.
For the title, would this be a title? Average price of gas?
Yes. 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 It was perfect. It was perfect.
It said I didn't have titles.
Where did you put it? Yeah, the title usually goes right up in here. I thought that was the definition of your variable there. Was it the average price of gas on the y-axis? Is that what you put on your y-axis? Yeah. Okay. So that the title goes right in the center.
It's separate from the label.
Separate from the label. So for example, so here, Derek on his, this was a wild unit. You want to hear this unit? The unit on the y-axis here was the amount of natural gas used by the United States in millions of million cubic feet. Millions of million cubic feet. So that's trillions. Along here was years since 1950. Okay, so the title of his graph is the 1950 to 1970 natural gas boom. Okay, those are the years he collected his data over, and it's talking about the gas boom, natural gas boom. All right, so but it's not one of his actual units from or definitions of his variables. Okay. All right, so I want to move on with today. So again, please pass that back in on a separate piece of paper. I need to make sure I can look at what you originally had. So if you missed that, please do not touch the green pages at all. I said that earlier. I want it on a separate piece of paper. So Taylor, you can talk to me after class, okay? All right, so today we're going to finish up the piecewise function idea and do some work on that as a group. And then we're going to cover this idea of the average rate of change, which is an interesting idea, and it's particularly important when you go on to 108 and Taylor, just don't touch anything, okay, right now, because I'll need to make some notes on this, okay? Just let it be, okay? All right, and before you all scoot out of here, I hope you have a very relaxing spring break, and if you're lucky enough to be going somewhere fun and luxurious, I hope you have a great time. It starts as soon as your classes are over today. For some of you, it's already started, right, in your heads anyway, mentally, but you come back March 25th, okay? All right. Okay. So this is an example of an integer in math, of a function in mathematics that's a little unusual. It's defined in pieces, and the piece is a constant over an interval. They're little horizontal lines over different parts of your x-axis. And it's called the greatest integer function. Some places, if you were to look this up, say on the web, you might look up the floor function. That's another name for it. There's actually a function called the floor function and the ceiling function. Okay, so we're going to look at the floor function, and this is how it's defined. Notice the symbols here. There's two different symbols that indicate the floor function. One looks like a bracket with the top missing, just has the bottom part of the bracket. That is to sort of tell you the floor, right? So you could probably guess what the symbol for the ceiling function might look like. What do you think the ceiling function would look like? The reverse, right? The top part of the brackets are there, but not the bottom, okay? So this is like page what, Taylor? Where are we? 33, okay, okay. The other symbol, and this is the symbol that your book will probably use, I think this is the one your book uses. It looks like a bracket, but it has two vertical sides, okay? That is also another symbol for the greatest integer function. So let's look at what it means to be the greatest integer function. So it means that whatever number goes in between here, so I'm just going to use this because it's easy to use, easy to write, the little bracket like that. So, and we're going to start with this so we try to understand what it means. This says, find the greatest integer. Well, first of all, do we all know what integers are? Yes, numbers. No, it's not a fraction, so that's a good thing to start with. It's definitely not a fraction. So let me scoot this down. This is sometimes a scary thing, you know, when the math teacher asks these questions, you know, integers. Here's your set of integers from -10 to 10. Okay. Kind of the numbers you like to work with, right? Okay, positive, negative, and 0. All right, no fractions, no irrational numbers. In fact, most of us never think beyond integers, but there's a whole slew of numbers in between each one of those integers, right? So now you get to kind of really think in terms of the numbers you like to think of. All right, so that's a set of integers from -10 to 10. Often what we do with our graphing calculators for our windows, right? The standard window. Okay, so this says, tell me what is the greatest integer? So let's actually put this right down here above our little table here. Where would 2.3 be? About right here, right? Here's 2.3. So tell me, what is the greatest integer less than or equal to 2.3? First of all, is 2.3 an integer? No, it's not an integer, so the answer can't be 2.3. So what's the greatest integer less than or equal to 2.3? So look on that little graph right there. What's the greatest integer less than that? 2, right? So that would be 2. Okay. What if I was 2.99999? What would my answer be? The greatest integer. So where's 2.999? Oh, right there, right? 2. Okay. The greatest integer less than that. What's less than that? 2. Same answer. Okay, I tricked you. And what about 2.0000000000001? Like I can't even like put it in there. It's so close to 2. It would still be 2. And what about 2? What's the greatest integer less than or equal to 2? 2. All right. So suppose we wanted to graph the greatest integer on the domain from on this domain right here from 2 to 3. So I go up from 2 to 3. I go up here and I say, okay, 2 to 3. So here's 2 and here's 3. If I go into my greatest integer function as the number 2, I can come out being 2. If I go into my greatest integer function being the number 3, what do I come out to be? 3, right? So, but if I'm any number right in here between 2 and 3, I'm going to get the tag of being a 2. So I'm constant. Over this interval, I am constant. I'm 2 all the way until I get to the integer 3. And now I'll have a different definition, because at 3, what will my value jump up to? 3. There we go. And no matter what number I am between 3 and 4, my output value will be 3, but at 4, I'm 4. So I've got to jump up. From 4 to 5, I'm defined to be 4, because that's the greatest integer less than all of these numbers here. And then I jump up. So you notice there's a little pattern going on here. Okay. If you're a fraction between 0 and 1, you're going to have the identity or the output of 0, because that integer is less than a half or a quarter or 3/4. Okay, so now the tricky part comes in with, what about an interval between -1? What happens right in here? So let's try it. Let's pick a number between -1 and 0. Give me any number that's not an integer between -1 and 0. -0.5. Okay. So I want the greatest integer that's less than or equal to -0.5. So look up here on your number line. When you're less than, what direction do you move? Left. So here's -0.5. What is the greatest integer less than or equal to -0.5? -1. So when you're on this interval, this is what you would look like. Okay. And so this just continues, and you can just try some of these for yourself. This continues in this pattern forever and ever. This is what we call a step function, because it looks like a bunch of steps. Okay. So if you were to actually graph this function and you were to create a table, notice you can't possibly put all of your input values on any one of these domains, pieces of a domain here. That's why it's called stepwise, because it's every part of your domain's been chopped up here for all the values between any of your two integers. So when you write your input, you express it as, here's just an example. So that tells me, what do I do with all of the x values greater than or equal to 1 and less than 2. So I say here, here's all my x values greater than or equal to 1 and less than 2. And what did I define them to be? I go right up here, I'm at 1. So they all get the output of 1. What about all of my values from -1, x is greater than or equal to -1 but less than 0? Well, here's -1 to 0. I'm defined to be -1. So notice when you input a table for this, it's actually an inequality. Some of you, I mean, I haven't seen it like this, but I would be fine if you wanted to do this kind of thing, because this actually shows you with your interval notation. Notice at 1 you're including it, so at 1 you've got a closed circle. At 2 you're not including it, so you have an open circle. So if you wanted to do a little interval notation there, that would be fine with me. Okay, so that's your greatest integer function. This is in your book. And then they gave you an application of this that had to do with the cost of a cell phone plan. If you ever heard, it's so many, like, and when you rent a car, so many cents per mile or any fraction thereof. So if you drive, if you would be in charge per mile, the greatest integer function would say, we're only going to charge you for the number of miles greater than or less than wherever you are. Okay, the integer value. So if you went 202.3 miles, they would charge you for 202. So any fraction thereof, it means an integer less than or equal to that number, the greatest integer less than or equal. So these are often used in calculations where you can get fractions of time. Although I'm not sure, I've got to check, but the one the book gave you has to do with telephones. And I think with telephones, if you're, say, between 1 and 2 minutes, I think they charge you for 2 minutes. I don't think they charge. If you're on the phone for 1 or 2, they round up. So that would be your ceiling function, where they round up to the next integer. So anyway, this is kind of an odd kind of function to kind of wrap your head around, and it just takes some time doing these sorts of things for yourself, okay? And the book does a pretty good job with this function, okay? Any questions on anything I did here in terms of the actual graph that you can at least articulate at this point? This one here or this one? Yep, it says if, so imagine the number line right here, Michelle. If I'm a number, if I'm any number greater than or equal to 1, but less than 2, any number in this interval gets mapped or gets assigned to the integer that's less than or equal to it. So the integer less than or equal to anything here is 1. The integer less than or equal to any number on this interval is -1. Okay? Notice where your closed dots are. They're all on the left-hand side of every little segment. All right. Did I do that right?
Yeah, it looks like a staircase.
Okay, so everybody agrees that what I did is correct. It's less than or equal to, okay. All right. So the next thing we're going to talk about is the average rate of change between two variables. Often functions, the usefulness of functions is that you can talk about the rate of change between your variables. Now we're very familiar with the idea of rate of change. What has rate of change been called so far for a very particular type of function that you all know and love? Slope, right. The slope of a linear function is a constant rate of change. So if you had a function that said, you know, you were tutoring and you were making $8 for every hour you taught, then you would have a straight line and you would know that between any 2 points, between these 2 points, if you connected those 2 points, you would get the slope of that line, and you would say the change in my y values over the change in my x values would be my rate of change. So in this particular case, 40 minus 24 over 5 minus 3 is 16 over 2, which is 8 to 1. That's your $8 for every hour. Okay, I've noticed a lot of you are very weak on interpreting slopes. Clearly, I didn't have you for Math 106. Your slope is the rate of change between two variables. So in this case, my y value is money, and this is hour. So if I were to interpret that slope of 8, this function or this particular equation could be simply written like this, 8x. I would say 8 divided by 1 represents my wage increase of $8 for every hour, the increase of hour that I work. It's $8 per hour. Okay, so here we have a different relationship between distance that an object falls. If I was on any high spot and I just dropped an object, I didn't throw it, I just dropped it. So what's acting on it in terms of making it fall? Gravity's acting on it, okay? And if you wanted to graph what the distance of that object was over time, it can be explained by this function. 16t squared, 16 times t squared. So what does t represent here in words? Number of seconds, thank you. Can you keep saying number of seconds what? The object has been falling, right? No, just t itself is just the number of seconds the object has been falling. The rule or the equation you assign to find the distance is going to square that value, but t itself is a linear measurement. It's just time, number of seconds. It's not a t square. I'm not defining t square. All right, what does d of t represent? What does d of t represent in words? Distance times time. Remember, when we use a functional notation, this doesn't mean d times t. Okay, hang on. Distance times time would be written just like that. Distance times time, okay? But d parentheses t doesn't mean multiplication. Someone else want to raise their hand? Let me know, Zach. And what does d of t mean in terms of this problem? What would I be finding? Okay, and in words, what would that be? The distance, and how are we measuring that here? Did I tell you up there? I didn't tell you, did I? Okay, the distance, let's say here in feet, the object has fallen, right? Or in what? In t seconds. Okay, because you have to have an input. So you tell me how many seconds the object's been falling, I'm going to tell you its distance. So I input t, I put it into my machine, which is going to take t, square it, multiply it by 16, and out comes my output, the distance for any particular time. Okay, so let's take a look at what this would look like on our graphing calculator. So first of all, let's suppose we were going to the top of the Empire State Building, which is 1,250 feet tall, and I wanted to figure out, I wanted to graph this. But before I do that, I'd have to figure out some sort of window. Where do I start? What value would I start my x min at? Or my t min, sorry. T min, right? Because my function's in terms of t, right? So where would I start my window, do you think? 0. How far up am I going to go, do you think? It's got to, how far will this object have fallen when it actually hits the ground? 1,250 feet, right, Ed? So I don't know right now off the top of my head how long it's going to take to know what my graphing, what my xt max will be here. But I could guess, or I could use a little bit of algebra. 12,050 equals 16t squared. T squared equals 1250 divided by 16. And since I'm only talking about time now, I know t is going to be just the positive square root of that. So that will give me an idea of where I could end my range here. So let me just see. That's a very quick calculation. Oops, I've already done it for you. 1250 divided by 16. And now I take the square root, right? Oh, what did I do? Square root of my second answer. Did that stay in my calculator? Right. About 8.8 seconds to drop from the top of the, okay? So t is about 9 seconds, so I might make my window from 0 to 10. What about my height? What would that have to go from what to what? What's the smallest height I can have? Smallest distance that it can go. What's the smallest distance? The smallest distance it would go is 0 before I drop it. And then my maximum here would be 1250, but I might throw in something like 13 or 1400 just so I can see the whole graph. So let's use our graphing calculator. We're going to graph this. What does your graph reveal about the rate of change between the distance an object falls with respect to time? So at your seats, put in y equals 16x squared, and then actually graph it over that window and see what you get. So let's take a look at the graph. Here we go. All right. Let's capture this. So this represents the distance you're falling with respect to time. So here we go. Here's the graph. So we have t along this axis and the distance with respect to t along that axis. So what does it reveal about the rate of change between the distance an object falls with respect to time? So in other words, I gave you a little hint. Is it constant? Is this object, is the distance it falls over any particular time period constant? Some say yes. Some say no. Some say, I don't know, I'm waiting for vacation to start. What would it mean to say that the distance this thing falls, the rate of change between the distance this thing falls and its time is constant? What would it mean? It would have to be a straight line. This thing, look where, I mean, at 0, it's 0. It starts off very slowly. In other words, over a particular time period, it hasn't gathered much distance, but gravity's acting down on it, and it is, its distance, its rate of speed here is increasing over time. So the distance, so how would you look at that? Let's just take a look at, let's say we're going to go out 3 seconds. Let's see what our distance is after 3 seconds. Let's find that. 16 times 3 squared. Okay? And let's go from 3 to, say, 5 seconds. 3 to 5. So I want you all to help me calculate this now. Some of you might maybe can do it real quick with your calculators. So what's the distance this object has fallen after 3 seconds? Do I have a second on that?
Yeah.
That's what yours says too as well. Okay. How about after 5 seconds? What? 400. Okay. So if I connect those 2 points with a straight line, and I find the slope of that straight line between those 2 points, I'm finding the change in distance over the change in time. What is the change in distance over the change in time usually called? The word. The rate, or normal everyday language, what do you call your change in distance over time? Speed, right? Change in distance, feet or miles over time per second per hour. That's called your speed. Okay, so we're finding the average speed this object is traveling from 3 to 5 seconds. That's what we find when we calculate the slope of that line. Okay, so let's find that change in distance. 400 minus 144 over 5 minus 3. 400 minus 144 is 256, I think, over 2. And what's that? 128. Yes, everybody agree? 128 feet per second. So between these 2 points, the average rate of speed is 128 feet per second. Now, if this was a constant relationship and I went from 5 to 7, what would be the average rate of speed? 128. But it looks like it's not a straight line from here to there. Okay? It's increasing. Your average rate of speed is increasing over time here. Okay, so let's check out 5 to 7. Let's go 5 to 8. Let's go 5 to 7 so you can see the same time and change. So let's go 5 to 7. So 5 to 7, we already know the point on our table. We know if we're at 3, our distance is 144 feet. At 5, it's 400 feet. What is it at 7? What is it? 7 what? 784. So let's find the change in distance over the change in time. Now, folks, I just want to show you your slope calculation. The notation looks a little different because you have functions. Usually you're used to putting here y2 take away y1, right? But what are we looking at here? We're looking at d of 5, the output, the value of my distance when time is 5, and we're going to subtract from that the distance when my time is 3 over 5 take away 3 seconds. So what's my distance when we've been traveling for 5 seconds? 400. Oops, we're doing 7 and 5. Sorry. Okay. So we can say now d of 7 take away d of 5. That's no different than the change in my y values. It's just a different notation. And 7 take away 5. So let's see what I get. D of 7 is 784 minus d of 5 is 400 over 2. We're still looking at 2-second intervals. And 784 minus 400 is 384 over 2 is 192. Now I'm going over that particular interval, I'm traveling at 192 feet per second. So this certainly isn't a constant relationship. And if you've never been able to answer that question by looking at a graph, the only way this rate of change could have been constant is if this was a straight line. Because between any 2 points on a straight line, that rate, this speed would never change. It's like I'm driving at 50 miles an hour, right? For 5 hours. Well, if I graph that between any 2 time periods, if I never changed that 50 miles an hour, I would get a straight line relationship. Okay? So what we're finding out here is the average rate of change between the distance and the time. Okay? That's what we're finding. So your average rate of change formula. You're used to it looking like this. Okay? So let's say we have a function f of x equals, I don't know, let's call it, say, x squared, for example. And I wanted to find the average rate of change from x equals 2 to x equals 5. Okay? Then all I do is I say, what is the value of my function at 5? What is my output, my y variable? What is my output when I'm at 2? And then I look at the change in my 2x values. So f of 5 here would be 5 squared minus 2 squared all over 3. That would be 25 minus 4 all over 3, which is 7. So between those 2 points on your parabola, the average rate of change would be 3 to 1. Now you look at any other 2 points on your parabola, and what would you expect the rate of change to be? The same or different? Different. Now in your homework, they want you to find net change. The net change is just this numerator. That's the net change. It's just looking at the change in your 2 y variables. And it's on page 177 in your e-textbook. You need to look it up. Okay? So what I'd like you to do now is I'd like you to go to the two froggies. Frida and David, and work together on this. And over vacation, make sure you can do the problems on pages 36, 37, and 38. Those are all of your piecewise. When you come back on page 36, that starts off with, we did this in class the other day, the Academy of Music. 37, there's like 4 problems. If you can work through these problems, and I've got answers on the back, try to work it out without looking at the answers, okay? You can work through those problems successfully, and you should be in pretty good shape for any type of assessment question on piecewise functions. Right? So you got 10 minutes. Look at David and Frida here, the two frogs, and this will help you with your rate of change calculations. What page is David and Frida on? 35. You gonna hang out with David and Frida? Yeah. Oh, I did find a calculator. What did I do with it? I had it in class the other day. I'll go look for it real quick. You want to use this one right here? Would you recognize it if you saw it?
Yeah.
Okay, good.
It's keys.
Okay.
Master keys.
Okay. Scoot in a little teeny bit for me. Okay. So your flag up here, Jalen?
Oh.
No? I think one of the frogs actually almost took a rest, right? Not quite, but.
Slow pace.
So which frog would you be, Shane? Would you be Frida or David, do you think?
I don't know. It depends on my mood, I
Yeah?
guess.
Okay.
I've been known to be both.
Yeah? Okay. Slow and steady wins the race?
Yeah.
That's Frida, right?
Linear Frida.
Yeah, linear Frida, right.